Let's go over a couple of examples for this week's discussion quiz. In question 1, we'd like to find the differentials dy for these two expressions. So this is really two separate problems. So to start with, y is equal to cosecant of 5x. We're going to find dy. And for a differential, we'll put the dx on the other side of the expression after we take the derivative. So we're starting with cosecant, and that's a composition of two functions, so we need to use the chain rule. The derivative for cosecant is negative cosecant cotangent. Because 5x is in place of x, we're going to write 5x. But by the chain rule, because this is not just x, it's 5x, we have to multiply by its derivative, which is 5. The very last step is to put a dx on the end, and this is the differential dy for this equation. Let's repeat that for this function. Y is equal to, this is called a power tower. It's 2 to the 3 to the secant of t. All right, I'm going to copy down the equation. That is y is equal to 2 to the power of 3, which is raised to the power of secant, and I'll use parentheses and say secant of t. To find the differential dy, we're going to start by differentiating this equation here. And I can see we have a composition of two functions. We have 2 to the something. The rule for taking the derivative of 2 to a thing is you have 2 to that thing, so that's 3 to the secant of t, but you have to multiply by the natural log of 2. So this first thing here is just the derivative rule for 2 to a power. Now, by the chain rule, you have to multiply by the derivative of just this exponent. But the thing to point out is we have yet another composition, meaning when we take the derivative of this entire exponent, we're going to have to use the chain rule one more time. So we have 3 to a power. The derivative rule for 3 to a power is it's 3 to the power, and the power is secant of t, but we multiply by the natural log of the base, which is 3. Again, because this thing was not t, it was secant of t, we have to multiply by its derivative. The derivative rule for secant is secant times tangent, and here the variable is still t. The last thing to do is to put the d, in this case t, at the very end of the expression, so just be careful about that. This one's dt because the function for the variable input was t, whereas this one was x. These are the two solutions for question 1. Question 2 is a related rates example. It says the area of a square is decreasing at a rate of 4 inches per second. How fast are the sides of the square decreasing when the sides reach a length of a single inch? It says to express our answer as an exact value. It goes on to say that when solving this problem, we should define all variables, set up any necessary equations relating those variables, and then state our answer with appropriate units. And it's nice here that we're given, hey, the formula for the area of a square, which is a is equal to s squared, where s is the length of each side. So just to maybe draw a diagram to start this problem, we have this square, and the area of it is decreasing. So this thing is shrinking in size. Well, that means the sides are also shrinking, and we want to connect those rates to each other. So A is the area, and each side has length s. So I drew these variables in the diagram, but let's actually write out what they are. I'm defining s to be the length of each side of the square. And I'll also note that the units on this are going to be in inches. Again, that's because I see inches as the unit of distance in this problem. The other variable that we have is a, and this is the area of the square. So area of the square, and the units on this are going to be square inches, because if you multiply the two sides together, that's inches times inches, which is inches squared. Okay, now that I've defined my variables, to connect these in an equation, the equation was given, but I'll just write it out as a is equal to s squared. To introduce the rates of both a and s into this problem, I'm going to take the derivative of both sides of this equation with respect to t. The left side's simple. If you have a single variable and you're taking the derivative with respect to, in this case, t, it is simply dA dt. On the other side, we have to be careful in that we have to use the chain rule, or bring down the 2, copy down the s. Technically, you would subtract 1 from the exponent, which I won't write. But by the chain rule, you have to multiply by the derivative of this thing, which is ds dt in this case. So from this equation, we now have this brand new equation that's connecting the rates of change of the sides to the area. Since we've defined our variables, I'm just going to go back up here and write out, well, what is ds dt? Do we know what this is equal to based on what is stated within this question? And you can do the same thing for dA dt as well. What is dA dt? The number here is telling us how the area of the square is changing, and it says it's decreasing. This means that dA dt is -4, and that is square inches per second. Now, ds dt is how the lengths of the sides are decreasing, and we're actually not given that piece of information. In fact, this is the thing that we'd like to try to figure out. It's going to be some inches per second. And we want to know this when s reaches 1, so when the side length is 1. So I'll just make a note of this. We want to find this when s is equal to 1 inch. Let's not confuse this s, which here means seconds. S here is the length of the sides. Okay, with all this being said, if we go back to this equation, we can put 1 in place of s. We can put -4 in place of dA. And the thing that we're going to solve for is the thing that we want, which is ds dt. So that is dA dt is -4. We have 2 times 1 times ds dt. If we rewrite this equation, you can divide both sides by 2. So like in this equation, we can divide by 2. And we get that -2 is equal to ds dt. And let's just be careful to interpret this answer. This negative means that the sides are decreasing. And this 2 is 2 inches per second. So I'm just going to conclude this problem by saying the sides are decreasing. Again, the decreasing is referring to the fact that this rate is negative, so we have a decreasing rate. So the sides are decreasing at a rate of, and that would be +2 inches per second.